Oh, what's this? Uh-oh. It looks like I made a loop and logic error. Well, I guess... Oh my god, we're still back in this. Look! Oh my god, it's so broken. Well, you know, if you make a mistake or an error in logic, there's only one solution. What's this? Oh no! Oh, I got hit by a spirit bomb of logic. Oh jeez. Oh, I guess this is over there. But yes, welcome Jedi Master. I saw you got a pop side thing coming up in a little bit. Good to see you, my friend. So apparently, let's go back to Hans. Let's go back to Hans because of course it took a programmer about 3 sentences to point out what was actually going on here. And I had actually, what he points out, let's go back over to our tab here. This guy, window, and X. Okay. So as we can see, Hans posted here, and this is something I was struggling to wrap my head around. I'm like, wait, the long story short is, even if you go to Wikipedia, you start going through different literature, and I was looking, I'm like, this looks like a trivial case, because I'm pretty sure a lot of this is obvious. And Hans points out it's literally baked into the definition. So the TLDR it's trivial and useful, in my opinion. And again, could be completely wrong. That's why we start off very often with our little conjectures, and let's get Professor Wolfram to say it so we can cover our butts as we conjecture ahead.
Although this is going to be weird, and it's going to be about a different
title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Ruliad. I don't think it rules them all. And it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyper-rulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
All right, so let's go right back into it. So as we can see, this is from Hans. His Twitter is linked in the doobly-doo. He's works on blockchain and stuff, so if that happens to be your type of thing, maybe you would enjoy following him. Again, I ain't your dad. All right, as we can see, Hans is saying that he happened to click on my video and thinks I am making a mistake. All right, the reduced play. See, the first thing here, at first I was going to say, because of course we tend to assume we're right and everything, H bar is defined. I'm like, that's not what H bar is defined as, but as you can see, he did a little thing, because this is normally the elementary charge squared divided by 4 pi epsilon naught. If you had H bar in there along with C, thus being a light in the vacuum, even if there's quote-unquote no true vacuum, that would normally be the fine structure constant. But all he did here, via the unreasonable effectiveness of algebra, is he just moved alpha, aka the fine structure constant, over there, thereby it equals H. Now this is something I remember, Thad had wrote this on the board, and I had been looking for this for a while. So as I was going through, I had saved it on my phone, but I completely forgot the little construction here, and then got distracted by other shiny things here. But this is correct, because if we go to our friend Wolfram Alpha, and we do, what was it? So elementary charge. So all this is that's either the charge of a proton or an electron, and since it's squared, it's going to come out to be a positive number there, because if you square a negative, you're going to get a positive, bada boom, bada bing. All right, and then he had the 4 pi, and then he had the electric constant, which is that epsilon naught, so electric constant, and then the fine structure constant times c, the speed of light. All right, so let's throw that in there. Go Wolfram Alpha. And as we can see, of course, it's giving us the same number. It's basically giving us Planck's reduced constant, aka h bar. Duh. So let's go back to Hans here. So as we can see, Wolfram Alpha defines the classical radius. To my knowledge, it was, if you take the mass energy and you were to put into, quote unquote, something along the lines of hydrostatic equilibrium, that's how you would get the thing out. So it defines the radius as elementary charge over 4 pi epsilon naught, the mass there, and then c squared. So let's do that there. So we got our elementary charge, and then let's put our mass term in there. So we're replacing alpha, aka the fine structure constant, with a mass term. So let's throw, it should be electron mass. I'll do c squared. Okay, and that looks like, oh look, the classical electron radius. Oh, and then what happens if we put in the proton mass? Oh look, the classical proton radius. Well, the logic holds. So essentially, this is, my first thought is, well, if you can calculate the Compton wavelength, which is Planck's full constant, so basically h bar times a cycle, certainly, so basically 2 pi, then you put in the mass and then times c in the denominator, you get the Compton wavelength. So it's about 4 times that. All right. So as you can see, if you multiply both times by the mass times the speed of light divided by alpha, the fine structure constant, you're going to get the RMC, so the root mean square charge radius, aka what we consider the actual radius of the electron, or I believe, well, electron's still thought of as a point particle, but basically you're going to get basically the Bohr radius and then the standard radius, aka that 8.4 something femtometers. Okay. So basically what he's saying is the identity is baked into the definition of the classical radius. This is not a new physical discovery. So listen, as much as I would love to say that, oh my God, I discovered this something else that nobody did, I'm like, it just lined up so well for so many digits. I'm like, this had to have been known. It's just when you're going through like the Bohr radius and the classical radiuses on like Wikipedia and everything, it's like, it doesn't straight up say that. But of course, it took somebody with a programming background to very succinctly describe what the heck is going on. Yeah. So it's basically not the codata value, although the codata value is actually for the CMS radius, RMS radius, sorry. Basically, it's essentially a unit conversion artifact, a definitional loop that links classical and quantum definitions via, but not a true physical relationship. Now, I would push back again. I had to like this because, well, he's pointing out what's actually going on. If we're going to be searching for truth, it's like, even if you have something and it happens to generally be your thing, if you're incorrect or portraying it incorrectly, we should be honest about that. So that's why we had to share it around. Because we don't want to do fake science. Oh, God, who knows? I put up enough things there where I'm like, oh, this is totally untrue. And then you realize while you're going through it, it's like you take a step back, you swallow your pride, and you move on. Why? Science is the search to be less wrong, or at least to cast off our misconceptions, as a Mr. Rick DeWitt would say. Again, swift recoveries to you, my friend. But I would claim that it's trivial. Yes. In a way that actually makes me feel a lot better, because it's like, all right, so there's actually something out there. And I had always I remember it was a couple of years ago, I'd asked that about something, because there was some calculations like, all right, the proton root mean charge radius. I'm like, what is that? Well, that's essentially what we know as the radius of the proton, according to our measurements. And of course, there were some problems with that because, let's just go over here. So, proton radius. Okay, let's bring this up. I can share with the class. All right. Okay. So, as you can see here, we have the proton radius puzzle. Let's just go into this. All right. Let's make it a little bigger so we can actually read it. There we go. All right, the proton radius puzzle. And again, it's from Wikipedia. Take it for what it's worth. Feel free to validate. All right. So this is, again, as far as Wikipedia knows, Relating the size of the proton. Historically, the charge radius was measured by two independent methods, which converged at a value of about 8.7 femtometers. Basically about 10 to the minus 15. All right. Very, very small. This value was challenged by a 2010 experiment using a third method, which produced a radius about 4% small. Now again, 4% don't sound like much. It's like, all right. If 4% of a pizza is gone, it's going to be a little bit there. You're probably not going to miss it that much. But when you're dealing with things so incredibly small, and we're attempting to use things like protons as the building blocks of chemistry and the things that we're actually using to make, microprocessors and stuff, accuracy and precision matters. Okay, so it was coming in at about 8.4 femtometers. So it's smaller than that. And then we have new experiments reported in about 2019. And then they had older analysis of data. But basically, what they're saying is, essentially, we were wrong. We thought it was about this, but it seems to be a bit smaller there. Okay, well, that's science. As we're able to probe deeper and deeper and get a better understanding of what's actually going on, our precision should increase. Now, here's the thing, and again, there's a lot more to this, but just an initial approximation that explains it. Now, I'm going to say it's trivial, but I'm going to claim it's still useful. Why am I claiming this is useful? Well, if we go over here, let's just do the real quick calculation, and we'll get back to the chat. I apologize. I'm such a terrible host of these things, so let's just do this. We'll do our whole, see, the speed of light times the proton mass. And then we're going to do, let's say, proton classical radius. And then we're going to divide by the fine structure constant, aka alpha. And structure constant. Okay. So we're going to do multiplication. Oh, hold on. I'm not even sharing the right screen. I apologize. I went to the tab rather than the window. Here we go. So here's what we got here. All right. So we just put it in the natural language because Wolfram Alpha can do that. All right. And then basically we're getting the magnitude of Planck's reduced constant, h bar. Cool. Why is this interesting? Well, if we open up another little thingy, all we're going to do is we're going to compare those radii. So let's do this. Take that off. So proton classical radius divided by proton radius. Okay. You get this answer here. I'm like, what the heck is that answer? Well, that answer happens to be about, let's do it the other way. It's a little bit more telling when you do this. So proton radius divided by the proton classical radius. It's about 550 off. What the heck could that be? Well, Wolfram Alpha, full disclosure, it's rounding right here. So that's not actually accurate. But if we do this one trick, let's just say if we did, 4, and then times the fine structure constant. Divide. Oh, look. 548.14 da. That's pretty dang close. If you were to round up at least to the nearest 10, that's going to give you 550. Why is this interesting at all? Well, if we take the proton classical radius, which, at least according to the data, we got a bunch of numbers for, and we multiply it by that, or you could always just do this. Dad pointed this out. You just do 4 of those. Sounds kind of orthogonal, if you would. So we're getting, divide. Duh. See? Oh, God, I was so wrong. Basically, you're getting the proton root mean charge square radius, aka the radius of the proton, which the interesting thing is it actually has the more updated thing about that 8.4 femtometers there, or 10 to the minus 16 there. So if that's the conversion factor, the interesting thing is, if we're taking that classical number that we've had for a good while, because I think we've had about 10 or 12 digits measured of the proton's mass for a good while now, this seems to be the conversion factor. 4 of those classical radii for the proton divided by the fine structure constant. The interesting thing is it's not giving us the old thing of that 8.7 number. It's giving us the 8.4 number, aka what, as far as we know to our best measurements, it essentially is. So that's why I'm going to claim, yes, that relationship, it is trivial, but I'm going to claim it's useful, because this gives us a method to at least attempt to conjecture and predict what the actual radius of the proton may be, utilizing a logical, coherent system. Now again, it could be wrong, but at least if we go over to codata proton radius, and we actually look at the measurement, because Hans was saying that that doesn't necessarily represent the measurement, and again, that's fine. That's true. That's totally true. And again, it took a programming mindset to very clearly explain it was trivial. And that's why very often I try to caveat my things in that, listen, I could be totally wrong. We conjecture ahead, because that's a conjecture. Could be totally wrong. It's a hypothesis. And hypotheses, most of the times, are wrong, because most things are wrong. If there's one thing we can be sure about, it's we're going to be wrong, at least most of the time. So let's go over here. All right, so at least the current proton RMS charge radius is from our 2022 data that was released last year in 2024. Don't ask me why. But basically, the proton RMS charge radius is listed at 8.4075 times 10 to the minus 16. Now, if you notice, these digits over here, that's 6.4, those are our error bars. Okay, so what that means is, within the errors, to the best of our measurement, it could flip up in the last 2 digits or flip down. So at least within this, well, that's a 6. Well, that's going to bring that up to a 4-1. And then we're going to at least have a 3 and then a 9 after that. What was our claim thing? All right, so 4.12. Well, that's less than 3 right there. So it is within 1 sigma and within the error bars. So that's why I'm going to claim that this is trivial but useful. And again, thank you to Hans for pointing this out, because again, I'd originally gotten this calculation because I viewed one of Dr. Unziker's older videos. He's like, well, this is an interesting relationship. I showed it to at least another individual that happened to be a mathematical physicist, and people seemed really surprised. So yes, again, it took a programmer to point out that within the logic system of Wolfram Alpha, what was going on. So again, is this a new discovery or anything? No. This is something known, and that's what I said. I'm like, somebody asked me, it's like, well, how did you come to this intuition? I'm like, Wolfram Alpha told me it was like 1 over 137, so I just divide by alpha, and then we got that result. So again, it shouldn't necessarily even be that surprising, but it was kind of like a used car. It was new to me, and thankfully Hans succinctly explained what was going on, so now I can register that into my knowledge base and feel, oh God, it's like, oh my God, so at least people know this, because I'm like, how do you literally have a matching of 9 significant digits and not notice? It's not like you have like 3 digits and you're going to conjecture that, okay, well, this is going to be equivalent to the magnitude of h bar or something like that. That's what crazy people like me do. So, well, again, we have to go by the data. So if future measurements happen to pan out and we get smaller error bars over here, and this ends up matching this for another couple of digits, well, maybe there's some there. Or it could just be a coincidence. But I just find it interesting. We're taking a classical thing, we're doing the conversion, and it seems to be hitting the numbers from our experiments, at least within the error bars. So again, we want to be open and transparent as much as we can. If you make a mistake, and again, I think it's a significant thing for at least me to be able to think about this in this method that, okay, maybe there is some relationship here. And again, this relationship, if it's built into the definition and it's just circular logic, it's like, okay, again, maybe it's nothing, but if it actually helps us with predictive powers, because apparently a lot of folks are very, very in the realm of we want to make falsifiable predictions. Now again, you might not agree with this. Maybe this is just an artifact and everything. However, if the measurements do bear out and they hold water, maybe it's something worth knowing. And again, the sheer fact that at least a couple physicists, like even when I asked that, it's like, I haven't had it explained to me like this at all. So this is something that, again, it makes me feel a little better because, okay, now there's a reason, and it's not just like I randomly stumble upon something. It was just Wolfram Alpha was guiding me through its calculational process. So, all right, let's get to the chat there. Yes. Hey, welcome, Cool Cat. Hey, Keisho. Good to see you, my friends. Good to see you, my friends. Yes. So I have to come up here and be like, I was wrong. Now, I'm not actually even sure if it was wrong because we have to follow the data and everything, but Hans pointed out, because even me, I was like, isn't this just like baked into like the classical and Bohr radius? So it's like when I was going through, let's see, Rotan, let's actually just bring this up, share screen, let's go, proton classical radius, all right. So as we can see at the physics stack exchange, they're going through here, and then you can get the classical electron radius, which is basically that number that we were getting before. So it's defined as, this is basically Coulomb's constant right there. So it's 1 over 4 pi epsilon naught, which is the electric constant, times elementary charge squared. You get the mass of the electron, you get the c squared in there. So basically that's what Hans said. He just explained it in very few words what was going on, and that really helped. So thank you. So Hans, he's one of the supporters of the Mystify Psi podcast. So we had been talking the other day, and he apparently has a blockchain model that seemingly seems to reproduce some of, I believe he was saying, the transactional interpretation of quantum mechanics. And some of the things he was saying really seem to be lining up with other smart folks that I have heard and basically what they're talking about. Okay. So it's like I notice when there are different folks that say different things, it's like, all right, I try to put in a coherent framework because coherence matters. Whatever logic you're going to be following, you want to follow it so it actually does make sense. Because if it doesn't make sense, well, it's not going to hold water. It depends on the arguments that you're trying to make here. I just find it interesting that you do this, you have a simple calculation, and it does seem to match with experiment pretty well. So again, maybe that's just a fluke. Maybe it is an artifact. If the data seems to pan out more, and we get a couple more significant digits, then we're going to have to follow it through. Now, if we were to accept that there was some there, all right, so what is actually going on? The reason I say this is because, well, number one, we only have, at least according to this, we got 5 digits. We got 5 significant digits, and the error bars are almost of the magnitude of the last digits right there, okay? But if we have something like this is a fairly clean calculation. Again, could be just totally wrong, but it seems to match with actual experimental results that we've got achieved. And that's how we ground ourselves to reality, because you always hear the Professor Feynman quote, if it doesn't agree with experiment, it's wrong. Now, that statement is essentially the scientific method, or at least when the clip I was listening to of him the other day, that seems to be what it is. Now, note, experiments can be incorrect. That's also something you need. So just because it disagrees with one experiment doesn't necessarily mean it's wrong, because occasionally, what was it? They were doing that thing where they were measuring neutrinos. Oh my God, it looks like neutrinos are going faster than the speed of light. Or an Ethernet cable wasn't hooked up all the way, and there was some interference which ended up skewing the results. And that's why you want experimental confirmation. That was the whole thing with the Higgs, because initially at the Tevatron, they had basically seen signs of the Higgs, but it took for the CERN's Large Hadron Collider to be constructed, and then you had both the CMS and the ATLAS experiments also coming back with similar things to help validate the discovery of something that we essentially called the Higgs boson. Cool. So just want to get that stuff out there, and again, I had to use the silly clip of, hold on, let's go to it because it was funny. All right, bring up this dude. All right, so we just, I have to share this just because it makes me laugh, because this is, I don't know, I feel like some folks on the internet, it's, again, you don't want to take yourself too seriously. And if you can't laugh at yourself, I mean, who can you laugh at? And I mean, number one, look at that. Look at that beautiful man right there. Look at those engaging eyes and everything like that. And this is obviously what he did to me. It's like, oh my God, I've been hit with a spirit bomb. I'm being blasted all the way there. It's like, you gotta have some fun with it. It's okay. And again, if somebody can succinctly explain something about what's going on, because my mind was still up there, I'm like, people have to know about this. There's far too many digits. And then he points out via here. It's literally a simple calculation. And then even when I was digging through like the Wolfram particle database and something there, basically I believe what they said is this is the estimated, taking the total mass energy of the charge of those particles, what we refer to as particles, even if that's, whether or not that's the best definition or not is another discussion, but essentially defining their attributes there. And it's basically, I believe the term was, they're estimating a sphere in hydrostatic equilibrium. Okay, so whatever that means. So essentially, sphere of balanced charge equivalent to its mass energy. All right, so that's what we got over there. And let's, I can quit through there. All right, get that. All right. So the reason, again, I'm still gonna stay by that it's trivial, but useful. Why might it be useful? Because if that equation and that relationship were to hold, number one, we just look right here, it's giving us a bunch of digits that we can totally falsify by experiment for the proton's RMS, or its charge radius, what we consider the radius of what we know as the proton. Cool. Now where this comes into play is, all right, we've got a couple of digits for the proton radius. Hold on, if we go back over here to physical constants, let's look up radius. We're gonna know something very interesting. We have 5 results here for radius on CODATA. Why is that? Well, the alpha particle RMS charge radius, the Bohr radius, the electron, the classical electron radius, the deuterium RMS charge radius, and the proton RMS charge radius, aka that number that we're looking at that seems to be about 4% lower than earlier experiments. Okay. What you notice is there's no neutron here. Why is that? So it's, let's look up neutron radius. All right, so what do we got? At least the AI overview, it's about 8.8 femtometers. All right, however, it's important to note that this is the mean square radius of the neutron. Mean square? Wait a second. Oh, is that why there's a factor of 4 there? I don't know. You could have 4 things and that would make a square. I'm just saying again. I'm sure there's a much deeper explanation. That's just where my mind as a dude on the internet kind of goes. So let's go over here. So let's go to the neutron on Wikipedia again. Initial source. Feel free to dig into the other deeper data here. But all right. So the mass we seem to know really dang well. It's a little bit more massive than a proton. Okay. After about 14 and a half minutes, it seems to decay. We don't know why. Magic? I don't know. So it's got 0 net electric charge, even though there's some interesting things that go on over there. It's been 1/2 fermion, blah, blah, blah. Okay, so is there a radius here? There doesn't seem to be a radius. Why is there no radius? Well, at least for the proton and electron, those happen to be charged particles, as far as we know, don't seem to decay. A neutron has 0 net electric charge, okay? It doesn't mean it doesn't have a magnetic moment, which is also interesting, something with poles and stuff like that. Again, I'm not going to pretend like I know all that or anything. But let's look up radius. Okay. So the neutron has a mean square radius of about 0.8 femtometers. That's interesting. Why? Because it seems to be smaller than a proton if we were going to do that. Which, to be fair, it actually makes a lot of sense. Why? Well, once you get to a neutron star, if you add mass to a neutron star, it does a weird thing. It gets smaller and smaller and smaller. So the more small a neutron star is, the more massive it is. But we're adding more stuff and it's getting smaller. That seems very weird. That seems almost unintuitive, unless we assume that maybe a lot of our physics and stuff for neutron stars might actually have something going on. There might actually be some there, so to speak. So let's, because the interesting thing is, if we assume this relationship were to hold, what might we be able to do? So all we do is we go over this, and it's like, all right, well, if h bar seems to be the relationship, let's change this. Let's put in the neutron mass, and then since we have, the last time I had checked from some other sources, we have 0 significant digits for the radius of the neutron. We are unsure. We think it's about 0.8 femtometers. Maybe it's 0.79. Maybe it's a little bit bigger. We seem to be unsure. So all we're going to do is, due to the overwhelming effectiveness of algebra, we're going to solve for x meters. And if we're going to solve for x, we need to have this equal to something. We're going to set it equal to the magnitude of h bar. Let's see what we get. Okay. Oh, what did I do wrong? I still have proton in there, derp. All right, there we go. Now we can solve it, because now it's actually logical rather than throwing in an imaginary proton for some reason. All right. So you're going to get this number here. Really small number. This would essentially be the neutron's classical radius. All right. So let's take that same expression. So this is in meters. I'm going to put meters there. There are protective brackets here. We're going to put our factor of 4 there. And then we're going to divide by alpha. Did the alpha Feigenbaum constant because, well, it's because it can. So we're using alpha as the unit, aka the fine structure constant. So what do we get? Oh, 8.4 times 10 to the minus 16. That seems to be really dang close to the other number that we had, which 8.41 times 10 to the minus 16 meters. 8.40. That seems to line up with our intuition in that it looks like, at least the root mean square radius of the neutron, which colloquially we may refer to as the radius of the neutron, is a wee bit smaller than the proton. Oh, I guess neutron stars kind of make sense then. Because if all of a sudden whatever particles you have in there are getting condensed so far that you're going to overcome the electrostatic force, and you're going to get all those protons and electrons, and they're going to start to literally merge, and then, what was it, reverse beta decay or whatever it is. So they literally become neutrons. That argument might seem to hold some water there. Okay. And again, if we don't necessarily know what the actual, where is this? The actual radius is, if we got about one estimated significant digit, if any, of our estimate, again, here's at least a conjectured reason for what the radius of the neutron might be. And again, It might be completely bunk. We're going to have to follow experiment. But it does seem to be a wee bit smaller than the proton, so perhaps the proton and the neutron are signifying some point of balance, if you would. Because remember, flowing through all, there must be balance. Or at least that's the beginning of the Gray Jedi Code that I still drastically need to learn there. But I just find it fascinating that if we have the ability to look through these things, and perhaps we could actually make, this is a totally falsifiable prediction. If all of a sudden they come out, it's like, no, it's like 8.6 or it's 7.1 or something like that. Okay, that's fine. Then this does not hold. However, if we start to do more experiments and we see that it's, okay, it's about 8.4. All right, okay. And then if the next digit is like about a 0, and maybe this eventually will come up as a 1 because you round up to there, the 8.401 or so. If it's within the experimental error bars and we can continue to have digits pop out from this, maybe there is some there, and we can actually find interesting connections, and perhaps this expression holds. And again, this is a hypothesis on my part. I'm conjecturing here. And again, conjectures can be wrong. I'm not saying it's a law of nature. I was just following a calculation that had been presented by Dr. Unziker. I went down a Wolfram hole. I found some interesting relationships and talked to a few folks. It doesn't seem to be something readily known. And of course, somebody with a programming background took a look at it, and Hans was even saying the other day when we were chatting, he's like, oh, I don't really know the math and everything like that. I'm like, you say you don't know the math? You went through this, and, well, maybe it was just algebra. He just pointed out the logic and essentially the circular definition logic that led to this. That's great. It's nothing new. It's literally, by the definition, what's going on. Cool. Now, since that literally is the definition, that actually makes a lot more sense to me, because now I'm like, okay, I can intuit that this is a thing. And maybe you play around with some other numbers. So like, for instance, like, well, let's go over here. Alpha particle, RMS charge radius. Okay, we got pretty good data there. All right. So let's take this. Let's take that, and that's 10 to the minus 15. Let's just throw this in. Let's make a new thing for this. So we'll duplicate that. So let's do, actually, we could probably just do natural language. Let's just do this. So speed of light times the alpha particle mass times the alpha particle radius. Let's see, it might not have all the data on Wolfram Alpha. It's got a lot, hold on. Let's do alpha mass, and then we'll do alpha radius. If not, we'll just plug in, because it still uses a calculator. All right, so alpha mass, alpha radius, and we should get h bar there if this, okay, that's, all right, let's just do this. We'll do it manually. Times 10 to the minus 15 meters, and let's go back to co-data. We'll go back to alpha particle mass. All right, we got like 10 or 12 digits there. That's like 10. All right, we got 10 digits there. Let's throw this in. Okay, for the mass. And again, there is error there, so we go either way. Times 10 to the raised to the minus 27 kilograms. Just make sure that's right. Yep, 10 to the minus 27. It's on the magnitude of the proton. And let's go back. Ooh. See. Okay, speed of light, kilograms. And then meters. Oh. All right. Well, that's a heck of a lot larger there. Oh, hold on. We got to divide by alpha. Sorry. So, multiplication. Alpha is a unit. All right. Well, that apparently doesn't seem to work at all. Let's multiply it by alpha. Let's see what happens. Well, it's giving us a bunch of ergs and everything. Okay. So it doesn't seem to hold for that. That seems, well, at least for our more basic things, it seems to hold. We had to give it a shot, right? Yeah. So we've got kilograms. Let's try alpha squared. Because for the electron, it kind of works. Nope. 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 Totally off there. All right. So doesn't seem to hold for that. So it seems for more composite things, that law basically for, what was it? The deuteron, which is basically a proton and a neutron combined. I ended up having to put a factor of like Plouffe gamma constant in there, and it gets about the accuracy there. So again, could be just complete bunk, me just saying a whole bunch of things that aren't true at all, but that's, okay. So again, trivial, I'm still gonna claim for some things that it might actually be useful, because now we actually have some falsifiable predictions. Now, again, maybe there's absolutely nothing there, but it's also interesting because, well, again, I don't have a traditional background in physics. I say a lot of things, and most of the things I say are wrong. Why? Because most things are wrong. You just have to be open to casting aside our misconceptions. If you find something that's wrong, that's like, all right, well, we want to be less wrong because that's the search for truth. It's not like we're just going to be like, I like this, so therefore it must be that. It's like, that doesn't sound like science. That just sounds like personal preference. Now, if you want to give your opinion or personal preference, that's totally fine. Personally, that's why I do the whole, we're going to conjecture ahead. Buckle up. Could be wrong. It's when folks are very dogmatic in that they're saying, no, this must be the way it is. Why? Because I said so. Now, unless you're Stone Cold Steve Austin, that doesn't really hold much water in my opinion. So, hey, Sandro, good to see you, my friend. I read your work. I feel like I had read it before at one point. It's very interesting. It's very interesting. What the heck is temperature? It's the vibrational oscillation, the energy within atoms. Some may say it's energy without necessarily a coherent form, although there is some coherence there and everything. But as you were saying, there were some interesting experiments. I'm curious to see what some more experiments would say. And actually, you know what? Heck, if you want to come on at some point or another, I actually invite Hans on because he has his transactional interpretation. And don't worry, I see. I'm also in the position saying this. I'm not a prominent academic or anything. I'm literally a dude on the internet. I've talked with plenty of crazy people. And at least you seem to be following a potential logical process. Now, would there need to be more to try to bring things together? Would I like to see? Sure. So that's the thing. Send me an email to remind me because I'm very, very bad at keeping track of things. As long as there's something in my email box or something like that, I can at least remember and we can put together a little bit of a presentation, go through, and then we'll see what generally folks will say. And because that's the thing, we never know where a good idea may come from. And even if somebody postulates something, because a lot of time people, they overextend themselves in that kind of like, you may have found something and there might be something where it's like, all right, this is an interesting thing. It's the whole therefore aliens argument. It's like, all right, I saw something in the sky, I don't know. All right, therefore aliens. It's like, that's possibly the case. Now, there might be other alternatives, but it's like to go from unexplained thing I see in the sky to therefore aliens, there's a gap in the logic there. Now, I'm not saying it's not aliens. It could be aliens, but you see what I'm saying where it's like something unexplained, therefore aliens. It's you need to follow the logical process. Now, if you can go through that process and prove and show evidence that it is beings from another planet or something like that, that could be the case, but is that the most likely scenario? Is it possible? Because, I mean, what was it when, I think like the stealth bomber or something like that, when that was out there, people were like, oh my God, this is some flying triangle or something like that in the sky. It's like, a piece of military technology seems like a more plausible answer if you're talking about the stealth thing. Now, again, I'm not saying that there aren't things out there. I'm not going to talk about it because I happen to be an American, and it's not my MO to lessen the readiness of the United States Armed Forces. Now, people can feel free to disagree with that. That's my personal opinion. But all right, cool. So I look forward to chatting. But so long story short is I was wrong. What exactly I was wrong about is necessarily making the claim. Again, I'm not even necessarily sure it's wrong, because if it happens, at least for the proton, to give us the more recent radius, which, I mean, we've had, I think, how many digits have we had for the proton for its mass? Because, let's go right back over here. Let's go to like 2010. Table of adopted values, proton. Huh? Oh, they adopted those values. Derp. Table of all values. Just gonna do the one it says. Proton. Mass. Hold on. God. Where is it? So many ratios. Why do we have all these ratios? Oh, see, that's a good question in and of itself. Proton. Okay, we went through all these things. Let's just do. All right. Come on, proton. Come on, proton. Dun, dun, dun. There we go. All right. So the proton mass. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we've had like 10. I think we got about 12 significant digits now. Last time I was looking. So at least from 2010. Or at least the 2010 code data, we've had at least 10 significant digits for the proton. All right. So that measurement was about 2013, 2015, and then 2019 follow-up, and then I think 2022 reanalysis. I mean, and then it came out to be about 8.41 there. I mean, I'm just saying, just looking at, let's go back. Looking at this guy right here, I mean, if we've had 10 significant digits and we know it's basically equal to H bar, it's, long story short is couldn't we have kind of just done this and been like, X meters, and then set equal to H bar. Okay, and then that's the classical radius, aka if it was in taking the mass energy of the charge, putting in hydrostatic equilibrium. Again, that's what I believe Wolfram Alpha is doing it by. I could be wrong, and again, please correct me. If I'm saying something that's off, let me know, because this is how we learn. If you're wrong about something, well, then you want to be corrected. You want to be right. Now, the big thing is you don't need to be a dick about it. That can be hard for me because I am a dick. It's literally my middle name. But if we take this value right here, we do that whole little 4 times that because it's a root mean charge. We divide by alpha. Bada boom, bada bing, unit. Okay. If we've essentially had about 10 significant digits for the proton, and it's gone up and down, there's little fluctuations as we get more accurate. If this has been known, something like this, couldn't couldn't we have predicted this a while back? Or maybe not even all these digits. Take the last 3 digits off. It's like we're at least getting the first couple of digits that seem to fall within the error bars of our friend here. Because the error bars, 8.41, is within those error bars. Again, that's why I'm saying, yes. Is it trivial? Absolutely. It's a trivial relationship, but just because something's trivial doesn't mean that it is not useful. Because if we want to make falsifiable predictions, I mean, hey, this is a falsifiable prediction. It could be totally wrong. Now, if we continue to probe deeper, and we get better equipment, and we're able to explore this further and further, this particular relationship, and you start to see, okay, well, oh God, I'm sorry. Oh God, I stopped. I forgot I swapped over to the window. Hold on. Let's go to the window. I realize as I'm on something and I'm pointing something on, it's not changing. I'm like, okay. See, but this is a falsifiable prediction right here. So, and if that's what we want, this is a method of going about it. It's just that if we get better equipment and we're able to probe more and more accurately, because this is typically how science works, we develop science. The science helps lead to better technology. As our technological precision increases, we get to probe to greater and greater levels to understand what's going on better and better, more accurately. And if we're able to become more and more accurate about our precision, and if all of a sudden this previous measurement here, if all of a sudden, perhaps in the next couple of years, they have the CODAT update, we have a few more measurements, and that happens to be 8.41 or so, then I don't know, maybe there is some there. Long story short is, if you have a prediction and more people look further and further into it, and you end up matching more and more numbers within your prediction, that's going to increase your confidence in what might be going on. I know Professor Sean Carroll, this is one of the things that he stressed, is if you're going to have what's known as Bayesian priors. What's a Bayesian prior? Well, based upon your knowledge of what's going on, what do you expect to happen? And if you have information that contradicts that, well, maybe you're going to discount that. But if it's really good information, like if all of a sudden we have like 3, 4, 5 more predictions, and they seem to be hitting around this number, maybe there's something there. It's kind of like Sandro was bringing up, where there's some very interesting experiments that seem to have temperature affecting gravity. It's like, that's a very interesting thing, because, well, number one, as you increase temperature, the fine structure constant actually changes. Therefore, it's actually not quite as constant. And yeah, no, I have a chart that's got a calculation for the fine structure constant. Now, it has 7.5 sigma disagreement with experiment. It might be wrong. Now, there are reasons that give me confidence there's something there. Because perhaps, just maybe, there might be a kink in charge or something. Or there may be a very small error around the 7th decimal place for a particular constant, an Ampere's constant. I'm putting it out there. That rather than being exactly 10 to the negative 7, it might actually be more like 9.999992, 999 times 10 to the negative 8. Now again, on the 7th decimal place, that's where it deviates, but that very small little deviation there might actually lead to some interesting things. Well, the other thing is taking that value of alpha that Thad calculated, and then taking the value of the Planck charge that he had calculated within a closed form, a closed logarithmic-based form, they net out to elementary charge of the electron or proton. Now, the Planck charge listed on Wolfram alpha and the Planck charge that has are different. as well as the fine structure constant, does have a bit of a deviation around like the 10th significant digit. And even on the experiment that CODATA actually helped reference to give the more recent recommended value, even in that paper, they literally cut it off after the 9th digit and say, listen, at that time they had about 5.5 sigma tension with the Berkeley 2018 measurement, which up until that point was basically the best measurement. At this point, with recommended values, now they have about around a 7 sigma tension with it. So why might that be the case? Now, I can totally spitball and hypothesize. Ultimately, I don't know, but perhaps it is because there was a slight temperature difference. Perhaps depending on the temperature that you do it at, it's going to change. Perhaps depending on how you do the experiment, if you're including an additional dimension rather than charge itself, like if you've got a mass in there, I've read, and again, don't quote me on this, but it seemed like it makes calculations more complicated the more dimensions of physical measure you have in there. I mean, logically, that seems to hold up, but all I know is the fine structure constant, as far as I know, we have that standard, what is it? Elementary charge squared divided by, I'm going to do the whole thing, the 4 pi epsilon naught, aka the electric constant h bar times the speed of light, blah, blah, blah. Okay, we got all this. Now, perhaps you can intuit what this is. All right, that's giving us stats calculation has a 7 there, this has a 6. Okay, whatever. Now, this is how alpha is defined, because if you just go to alpha and we do unit, there we go. Alpha is a fine structure constant. That's its definition, its interpretation is the electromagnetic coupling. Now, you can look at this and then you realize there's a way to computationally reduce this. Why? Let's just follow logic. The fine structure constant is a dimensionless number. Okay. What could we take away? Well, basic logic, if you've got charge squared, that must mean this is charge squared. Oh my God, we're using basic logic. There we go. Okay, so I had to go through and actually do this. I'm like, what the heck is this thing? 4 pi, let's go back. All right. So we got this whole thing. We hit enter. What is this? Don't worry, I don't know what that is. I happen to kind of recognize this number because I'm a crazy person and go down so many Wolfram holes. But, all right, time squared times current squared. Time current, that's just charge. So these are squared, so that means, let's do the square root of that. What do we get? Oh, that seems to be the Planck electric charge. Oh, the Planck charge pops out. So that means this whole thing is just the Planck charge squared. So we can basically just apply just a little bit of computational reducibility and just be like, oh, so this whole thing is just electric charge, elementary charge over the Planck charge, all squared. Oh, look, we get the same number. Oh, don't that to me at all. Here's alpha. Again, don't believe me, only believe your lying eyes. I'm just saying. But as you see, alpha there, let's put it there. All right, so our result, blah, blah, blah. Our result, blah, blah, blah. Oh. It's the same number, folks. I'm just saying that. And that's the power of the whole, at least concept, of computational reducibility. Or just simplifying expressions via algebra. Because, well, if this thing is just a dimensionless number, that's a charge squared. That's going to be a charge squared. So you can simplify it. So the fine structure constant is the partitioning of elementary charge from maximal charge. Okay. Now, if you want to take more of the Professor Feynman look on it, he doesn't talk about this number. He's like, most of my colleagues like to refer to it as 1 over 137. Why? Because, well, if you just do 1 over 137, yeah, you get the first few digits. You get about the first 3 digits there, or significant digits there. All right, so it's an approximation. But what he said is, people like that because 1 over 137, it's pretty sexy in my opinion. 1 over 137, even though it's about 1 over 137.035999, and then we argue about the 10th significant digit. He likes to think of it like this. What is this? Well, this is the amplitude of the fine structure constant, because you square an amplitude, you get the probability of an electron to emit and absorb a real photon. Bada boom, bada bing. That's basically what Professor Feynman wrote. Okay, but this is its amplitude, and this is how Professor Feynman thought of it. This is also within Thad's notation, is Joe1, and when you take this number and you multiply it by the number that Thad has for the Planck charge, you're going to get elementary charge. Why? You just take this number here, multiply it by the Planck charge. Oh, look, we get 1 elementary charge. That's pretty neat. So it's basically the ratio of the partitioning of charge. Now again, this is nothing new. People have known this. It's kind of like the other thing. It's like, I just noticed this from going through, and it happened to come up, and then I think Fractal Woman, shout out to her. She had on John something. He was a physicist. He presented this, and Fractal Woman, she didn't happen to be aware. And she was like, oh, that's very interesting. That was the first she had seen it. Now, when that was being presented, I'm like, yeah, no, that's true. Because I just played around Wolfram Alpha, and you found that relationship. So again, is it new? No, but it's like a used car. It was new to me, and it helped me for developing my framework, because again, I don't have a traditional background in physics or anything like that. I'm a dude on the internet that happens to be very blessed and might be the luckiest son of a gun in the world. But it's about all we have. So, hey, Poindexter, we're just wrapping up right now. Basically, Hans destroyed me. He pointed out that there was a circular loop in the logic. Now, again, the results that we had, that I had promoted, they're trivial. Okay. Now, just because it's trivial doesn't mean it's useful. And I'm going to claim that it's useful because, well, it at least helps us. At least if we assume that was a thing as of about 10 years or so ago, we could at least approximate the magnitude within the error bars of the actual proton's radius, aka its root mean square radius, whatever that means. Okay, aka its radius. So, all right, that's about all I got. So I got to get back to doing some cramming for some Wolfram stuff and things, and take care of some other stuff. But other than that, hey, happy Memorial Day to all of you out there. Let's not forget all the folks that we've lost over the years, and try to avoid more conflict so we don't lose more folks than we need to. So, and hopefully none at all, but gotta be real. But take care of yourselves, everyone. Peace out. Stay safe.